Swayam Prabha. Digital India. Educated India.
Hello everyone. Welcome to the second lecture in this week on finite time stability. So what were we looking at last time? In the previous bit, what we've seen is the need for looking at non-Lipschitz systems or systems which have non-unique solutions at the origin. Yeah, so that's what we formalized, that the Lipschitz property essentially means that solutions exist and are unique. However, because we are looking at notions of finite time stability, it is not quite possible to have unique solutions from the origin, especially in backward time, and therefore we do not require it even in forward time. All right, so that is why we settled on the notion of having uniqueness in forward time everywhere but at the origin. So this is the notion that we choose to work with while defining the notion of finite time stability. Yeah, so that's the system we were working with. It's an autonomous system, right? There is no explicit time dependence. Yeah, so it's of the form y dot equals f of y, and on top of that we have that f is continuous in the entire domain containing the origin. F is locally Lipschitz in the domain but excluding the origin itself, and f0 is 0. This is simply the standard assumption that is required to ensure that 0 is the equilibrium of the system, right? Now this essentially guarantees that solutions exist for all initial conditions in the domain, and this Lipschitz condition essentially guarantees that the solutions are unique for all initial conditions in the domain but at the origin. Yeah, so we don't want to deal with the origin because there is possibility of non-unique solutions at the origin if you are demanding finite time stability. Yeah, right. Now we also defined the notion of finite time stability. And how do we define it? We say that the origin is finite time stable if there exists a neighborhood n which contains the origin inside the domain D, and a settling time function which maps the neighborhood to some time 0 to infinity. And the settling time is exactly what you would understand from it. It is the time at which the solutions go to 0. Okay, so obviously, as you can imagine, if you start at the so this settling time function essentially maps initial conditions to the time in which these initial conditions go to 0. Okay? So obviously, if you start at 0, since you are already at the equilibrium, you would expect the settling time to be nothing but 0 itself. Okay? And we also want that tx0 actually converges to 0 as the initial conditions converge to 0. Right? So notice that we never say equal to here, right? Because we do not want to look at initial conditions at 0, because our assumptions are on sets that exclude 0 or the origin. Yeah, so therefore we always talk of convergence to the origin and so on. Okay, so the second requirement is the second requirement of finite time stability is exactly the convergence, the finite time convergence. It says that if your initial conditions are in fact in this neighborhood excluding the origin, then we have unique solutions, right, which depend on initial conditions on this time interval, which is closed on the left and open on the right. So it is from 0 to tx0, and it is important to note that the solutions are never 0 in this interval, but as time goes to this value, yeah, we don't say equal to again, right, because this is not part of the interval. So as time goes to this value tx0, we say that x actually goes to 0. Okay, all right. So again, we are carefully excluding 0 from the mix. Yeah, we still want to converge to 0, but we never want to start there and so on. I mean, if you're starting there, that's considered as a special case where you're starting in the equilibrium and staying in the equilibrium. So there is no notion of, I mean, we don't have to, the finite time that we get is 0 anyway, right? The finite convergence time that we get is 0 anyway. That's what is encapsulated here, right? But we do not want to start at 0 otherwise. Okay, and we are always looking at converging to 0. Yeah, so limit also means converging to 0, right? And the last requirement is obviously Lyapunov stability, that I'm not going to repeat. We've already seen that Lyapunov stability is a requirement of asymptotic stability as well, and therefore it is but natural that a finite time stability notion would also have Lyapunov stability as one of the requirements. Okay, great. Now that we understand finite time stability, we have a few conclusions that can be directly obtained. Again, I'm not going to prove any of these things in this course. This is a very short introduction to finite time and finite time stability and sliding mode control. Right? So we are simply going to state a few results. Right? So the first sort of proposition, which is almost like saying an outcome of finite time stability, is what we state here. 0, if 0 is a finite time, I will just say if 0 is finite time stable for 1, or the system that we already considered, and we therefore have this, we already have this neighborhood n and settling time function t corresponding to this finite time stability definition, then what is understood is that the solution what is understood is that the solution is uniquely defined, and most importantly, it is understood that x0 is exactly equal to 0 for all t greater than equal to tx. Okay. All right. Yeah. So once you essentially how one would say this is that is uniquely defined for all x0 in the neighborhood n. Okay. What this is sort of trying to say is that once you fix an initial condition, you have a very uniquely defined path. And the important thing to remember is that, I mean, it's sort of understood just from the second piece here that once you will reach the origin in this time tx0, and what happens beyond time tx0? Well, you are already at the equilibrium, so you're not going to move unless there is some disturbance, but we are not considering the disturbance cases here. This is for the purpose of defining for a disturbance-free or a noise-free situation, right? The notion of finite time stability, right? Therefore, once you reach the origin, which is an equilibrium, you're never going to move. Therefore, that's what is essentially said here, that once you've reached the origin, you will always stay there for all time beyond, right? It makes sense. So this is not a very complicated notion, okay? The next thing to remember is that the solution the way this is written is, one has to be careful here. Actually there's a dot here, which means that the purpose of writing this dot is it's uniquely defined with respect to the time, right? And in here we say that xt, the solution is actually this is fine, I'll just keep the time here. It's evident that it's uniformly defined in time, right? And here I'm going to say it's continuous for all x0 in a neighborhood of the origin. Uniformly in time. Okay, so the first one says that the solutions go to 0 and will remain there forever. The second one says that the solutions are continuous in the initial conditions. Okay, this is important. Okay, and the final assertion of this proposition is that the function t of x0 is unique and again continuous in x0. Okay, so these are the important sort of outcomes from the definition of finite time stability. Okay, now what do we want to do? Obviously we've always seen that these notions of asymptotic stability, these definitions never really helped us, right? So what we really want to do is to sort of have some Lyapunov like conditions. Okay, so that's really what we would like to do, have some Lyapunov like conditions to characterize finite time stability as well. Okay, and so that is sort of what we are moving towards, right? So let's see how to state this. I'm wondering if all right, that's fine. So I will just call this Lyapunov like characterizations. Okay, I'm just looking at Lyapunov characterizations for finite time stability. Okay, all right, let's see now. Suppose I'm going to start with a more I'm just going to directly jump into the simpler case where and we already know the notion of v and so on and so forth at the Lyapunov function itself. So we define as before v dot of x as del v del x f of x for a v in C1, right? So if you have a continuously differentiable function v, then you can actually make this kind of a definition for v dot. Okay, all right, and this, by the way, this works even for this sort of special case where you have solutions which are unique but not at the origin and unique in forward time. All right, so this Lyapunov derivative idea is still valid here, yeah, that v dot turns out to be exactly this. Okay, all right. so what we need to understand is that important v dot is well defined in D removing 0, right? Because our solutions are well defined in D removing 0. Okay. All right. So what is the main result? So what is the main result? This is let me see, Lyapunov. I'll just call it Lyapunov theorem, right? I'll just call it a Lyapunov finite time theorem. And what does it say? Suppose there exists a V which is continuously differentiable and has the following properties. V is positive definite, right? This is a standard requirement. I mean, V is just seen as a function of some x. Therefore, we just need to verify the positive definiteness of V. We already know how to do this. Next, V dot is continuous. Well, V dot being continuous is already evident from the fact that V is C1. So V dot is negative definite on the deleted neighborhood, right? On the deleted neighborhood of the origin, right? So it's negative definite, but you need to verify only on the deleted neighborhood of the origin. So so you don't need to. So if you remember, negative definiteness had two properties that you check, has two conditions to verify. One is that it is, the function is 0 at 0, and it is strictly positive for all non-zero values. Okay, so in this case you just need to check that it is strictly negative for all non-zero values of the state. Okay, and that's it. Okay, and finally we want to you need this special condition, right, that there exists k positive and an alpha in 0 1 and a neighborhood V inside D, right, of origin such that V dot plus k V to the power alpha is less than equal to 0 on this V deleting the origin. Okay, if you have this, if you have these properties, then then 0 is finite time stable. Also, you can actually find or upper bound the settling time function, right, as tx0 is less than equal to 1 over k 1 minus alpha v of x to the power 1 minus alpha for all x in n, where n is as defined in the finite time stability definition. Okay, now it is important to sort of try to understand this result, right? I mean, the first one, I mean, the Lyapunov finite time stability theorem is not too different from the typical asymptotic stability theorem. In fact, the first and second look rather similar, right? So we require that V is positive definite and V dot is negative definite on this deleted neighborhood. On top of that, we have this kind of a funny convergence type of a condition, which says that there exists some positive scalar k and some exponent alpha between 0 and 1, yeah, strictly inside 0 and 1, yeah, never 1 and never 0, and a neighborhood V inside D of origin such that V dot plus kV alpha less than equal to 0, right? And if you have these three conditions, we are in fact claiming that you have finite time stability. Okay, in fact, if you would understand that from A and B, you would be immediately able to claim some kind of Lyapunov stability. Yeah, I'm not saying that I'm giving a proof of this theorem, but I'm just trying to indicate why this might work. Yeah, so from A and B itself, it's not difficult to see that you would have Lyapunov stability. The only thing that's left for us is to conclude the finite time convergence, and for that we can actually focus on this third statement, right? If I try to look at this sort of third statement a bit more carefully, yeah, it basically says that I have V dot is less than equal to minus kV to the power alpha, and if you see, this is a scalar differential inequality. Yeah, it's not differential equation, but it's a differential inequality, right? But it's not too difficult. I mean, you can deal with this in an exactly similar way as you would deal with an equality, right? So this will be something like, and simply again, this is because of the fact that V is positive definite, that we can all do this. So V is scalar value, so it's actually a scalar differential inequality, right? So I can actually do things like this and integrate both sides, right? And if you see, V alpha is less than 1, right? So I will get something like I will get something like V1 plus alpha, I guess, divided by 1 plus alpha. I'm just trying to see if I'm doing this right. No, I apologize. This will be V not 1 plus alpha, but 1 minus alpha, because alpha is in the denominator, right? So this is 1 minus alpha, and this is going to be less than equal to minus kt. Yeah, and so if I solve from here for the value of V, what am I going to get? I'm going to get V is actually less than equal to minus kt, or minus k times 1 minus alpha t, and this to the power 1 by 1 minus alpha. Right, this to the power 1 minus. Right. I believe that's okay. Right? And because, so this is 1 over 1 minus alpha, this is fine. And you know that 1 minus alpha is strictly positive by assumption, because alpha lies exactly between 0 and 1, right? So this is strictly positive, and therefore this is strictly positive as well, right? In fact, one can very easily show that 1 minus alpha lies between 0 and 1 as well, right? 1 minus alpha strictly lies between 0 and 1. Okay, so this is something that is right. Okay. And now if I want to if I try to equate this to 0, right? Suppose I equate this quantity to 0, what happens? Okay. All right. So, okay. So I see that the expression here has been given in terms of the V itself. All right. All right. Let me actually try to see. So the left hand side would have more terms. That's what I'm missing here. So what I'm missing here is like a V0, right? So where V0 is equal to V at x0, right? So in fact, I'm going to erase this and rewrite this carefully, because I'm going to have V to the power 1 minus alpha is less than equal to K V0. Yeah, that's what it makes sense, right? This has to be V0 minus K1 minus alpha to the power T. Correct. This is exactly it. And now if I make sure that if this equal to 0 happens, then I know that V is obviously positive definite, so it can never be less than 0, right? So I know that V will exactly be 0, right? V will exactly be 0, right? And if V is exactly 0 by positive definiteness, I also understand that my states will also exactly be 0, right? So that's sort of what I'm trying to, yeah, exactly. So this is exactly what it is, 1 minus alpha. This was also 1 minus alpha. So I should not miss this exponent here as well, right? And now from here, from this condition, I know that the T I need will be actually equal to V0 to the power 1 minus alpha divided by K times 1 minus alpha, right? And that is exactly this bound. Yeah, in fact this should be not x but x0. Yeah, this is not x but x0, right? This is a function of x0, right? So that's exactly what we get from here. Okay, so obviously this is the time we get, and this is obviously conservative because all Lyapunov analysis is conservative. We already understand that, and that is why we say that the settling time is always upper bounded. Yeah, you never arrive at an exact value of settling time function, but you usually almost always arrive at a upper bound for the settling time function. Okay, so I hope you understand now that from the first two you get the Lyapunov stability. That was the first requirement, and the next requirement was of course that you have finite time convergence, which you get from here. And in fact the expression for the settling time function is also rather easy to obtain just by integrating this scalar differential inequality condition, right, that we have written here. And just by integrating it carefully, I was of course not doing it properly to begin with, but now that you've done it carefully, there is also the value at time t and the value at initial time, right, at 0, and then divided by 1 minus alpha. So this integral evaluates to this, in fact, right? So this will actually be from, yeah, if you are being careful, this will be from v0 to v, and this will be from 0 to t, right? This definite integral, and that's what we've done here now, and you just get a minus kt. And once you have that, you know that you just need to equate this guy to 0, because that means that this is going to be exactly 0, because v can never be less than 0. And once you have that, you know that the t can be calculated like this. All right, okay, great. So we are left with a little bit of the converse theorem, and we'll look at a simple example in the next session.